All right, it's a little after 8, so I guess we can go ahead and get started. Does anybody have any questions about any of the homeworks or anything like that? I've put a whole bunch of files up and videos and all that kind of jazz yesterday and this morning. All right, so if nobody has any questions to ask about any of the homeworks or any of the topics covered in the video lectures, then I'm not sure that we need to have any more of class today.
Sorry, Dr. Hartman. Just getting this. Okay, first off, the problem 1 on homework 2, graphing everything, can we do that in LT Spice and then just rework it by hand after? Because I'm not sure how to start that by hand, honestly.
Okay, so let's look at homework 1, problem 2, you said, right?
Homework 2, problem 1, yes, sir.
Okay, let's see. Let me. $223 summer homeworks. All right, let me share my screen. All right, so we're given an input signal, right? So it says an op-amp based amplifier circuit has a closed loop gain of 12. What it means with closed loop gain isn't terribly important. I'm just telling you that there's a voltage gain of 12. So one thing that may not be obvious, I don't know, I think it's in the notes, but or at least I certainly hope it's in the notes, is that the voltage gain, oh shit, hold on. Let me open that back up. Oh, nope, it's right there. Okay. So the voltage gain is defined to be the ratio of the output voltage versus the input voltage, okay? So if we have a voltage gain of 12, and in part A, we're asked to plot the output waveform of the amplifier as a function of time based on the input voltage waveform shown below with the supply voltages of 18 volts and negative 18 volts. So let's look at this picture here, okay? Excuse me. The maximum value for the input voltage is 1.5 volts. If we multiply by that gain factor of 12, what's that going to give us, Gordon?
18, I believe.
Yes. And the minimum voltage is negative 1.5 volts. So if we multiply that by our gain factor of 12, we should get negative 18 volts. So if the supply voltages are plus and minus 18 volts, does our scaled version of our signal for part A ever have any saturation distortion?
Don't believe so, no, sir.
No. So for part A, the answer should look exactly the same as this, but with a different scaling factor. So what I mean by that is instead of having 1.5 volts here, it should be 18, and then down here, it should be 18, and let's see, so that would be 12, 6, negative 6, negative 12 like so. So the input and the output scale easily when we're within the bounds of our power supply voltages. Now part B, we still have the exact same signal, but we want to plot the output waveform of the amplifier as a function of time based on the input voltage if the supply voltages are 10 volts and negative 5 volts. So that means for 10 volts, which is going to be somewhere around here, we should see saturation. So all this stuff up here isn't going to show up. It's going to saturate at 10 volts whenever. And similarly, it's going to go into negative saturation when our output signal is less than negative 5 volts. So something like this. Does that make sense? So whenever our signal exceeds, mathematically, whenever it's supposed to exceed the supply voltages, we have saturation distortion. So overall, let's see if I can draw this, make this maybe a little bigger. For part B, well, that's not looking right. Oh, and I should have something up here too. This is what our output signal should look like. So anytime, like it's going to follow our answer for part A exactly, except when it's higher than 10 volts, and it's going to clip to 10, and whenever it's lower than negative 5 volts, and then it's going to clip or saturate to negative 5, based on the restrictions of our power supply voltages. For part C, it says, over what input voltage ranges will the amplifier behave linearly? And over what input voltage ranges will the amplifier saturate? And so I believe at the very beginning of my handwritten notes on lecture 3, I talk about what's called the linear range of an op amp. And it's simply defined by, let's see, I'm trying to remember if it's voltage gain divided by power supply voltage or the other way around. Power supply voltage divided by the gain. So is there any more room on this paper? Great. So Vn is going to range from VCC plus over AV down to VCC minus over AV. This is going to be when it behaves linearly. So for our case, this is going to be negative 5 over 12 is less than Vn is less than or equal to positive 10 over 12, which is, let's see, negative 416.667 millivolts less than Vn less than 833.333 millivolts. So as long as our input voltage is within that range, then we will not saturate, which means we're operating in the linear range. And we can actually kind of see that, right? If I get rid of all of these extra things and we're just looking at the input voltage levels based on where I've drawn them. So just shy of 1 is when we hit saturation distortion, positive saturation distortion, and just shy of negative 0.5 is when we hit negative saturation distortion. So things line up pretty good there. When the amplifier will behave in saturation is simply when Vn is less than negative 416.667 millivolts, and when Vn excuse me, is greater than 833.333 millivolts. So effectively, anytime it's not in the linear region, it will saturate. Is that helpful at all, since we just worked the whole damn thing?
Yes, sir. It is. Thank you.
All right. Any other questions regarding homework 1, 2, or anything else I've put up?
I do have a question, a general question on the homeworks.
Sure.
In most homeworks, you have rewritten the problem statement, and then under solution, you have the subtitle A or whatever part was working on, and then you restate the problem statement for that individual part. Do we have to do that, or can we just put part A and then go from there?
So let me show you what I've been doing. I've been converting my solutions to my tablet here. So all right, so this is page 1. So that's not very helpful. I think page 5 is when my stuff starts. Okay. So I have the problem statement for homework 1, problem 1. Wrote everything, and then solutions, and then I start my solution for part A.
Okay, now do we have to like label what we're doing? You say like using nodal analysis there.
You don't have to. I'm doing this for the benefit of at some point having a grader and things like that so that they can follow along. But like, you don't have to use nodal analysis for this problem. You could, for instance, use mesh analysis, and it would be the potential difference between A and B. So that would be the voltage drop over the 10 ohm resistor plus the voltage drop over the 20 ohm resistor. So if you did mesh for whatever reason, you could figure that out pretty easily. This is just the way I did it, and I like to be very meticulous in my solutions, so that way it's easy for me to find mistakes if and when I make them. Okay. So you don't have to go as gung-ho on labeling every single thing as I do, but it needs to be as, pretty clear so that I can follow along. So I did all my stuff for part A, then part B, because I was trying to find a current, I chose to use mesh. Set up all my equations, solved them. This is the delta Y transformation stuff that I talked about yesterday. So I was able to realize that this is a Y connected network. And then I have some stuff here on how to perform a delta Y transformation. So if I have a Y network, I guess this should be a Y delta transformation technically, so I'll change that. So I have a Y connected network. I know it doesn't look like a Y, but it is. And then this is a delta connected network. So using my transform, where I've defined how to get the delta resistances from the Y resistances, I find that I get 30 ohms for each thing. If I substitute that delta connected network back in, I can easily see that this 20 in parallel with this 20 makes a 10. So I have 20 in parallel with 30 in parallel with 60. And then there's the math for that, and so forth. And then here's my MathCAD for part A. Because the solve block was so big, I couldn't really fit anything else on that page. And then here's the solve block for B. And then the math for C, D, and E, because I like to use MathCAD for everything. Did that answer your question regarding the layout?
Yes, sir. Thank you.
Yep. Any other questions?
I do have one.
Yes, sir.
In regards to the videos, are some of them already on YouTube? Because I couldn't like find the like lecture videos.
So the ones from what we've like recording these sessions, the very first one that we did, but I haven't been able to put up the second one yet because I got busy yesterday, so I'm going to do that this morning. And then I'll also put up the one that we're literally making right now at some point today as well. As far as all of the pre-recorded lecture materials or whatever, like that's all that stuff's pretty much on YouTube, and I have links and all that kind of stuff in our Moodle site. So as soon as I create a video, I also put a link on Moodle to direct you to specifically that.
Okay.
Yeah. So that's one good. You won't have to search through all kinds of crazy gibberish. I will direct you to exactly what I'm expecting you to look at for each individual lecture and all that kind of good stuff.
All right. I just
Yeah.
need a clarification. Thanks.
Yeah, no problem. Just sifting through all that junk between circuits 1 and circuits 2 would be wild.
Yeah, that's what I was wondering. Like, I wasn't sure exactly which video to watch, but I didn't check Moodle, so I guess I'm stupid.
No, you're not. It's no problem whatsoever. But yeah, I have everything. So like if we go to the courses Moodle page, let's stop sharing real quick. Stop. And then start sharing. Chrome, I think. So if we go to the courses Moodle page, which I'm in right now, and then we go to this week's material. And I'm actually going to change the layout of the course on Moodle to be class meeting 1, class meeting 2, class meeting 3, all that kind of crap. So it'll be very, very easy to kind of follow along, and I'll work on that today. But so I have my handwritten notes for lecture 2, and then homework 2 is there, but it should actually, no, that's actually where it's supposed to be. Cancel that. Homework assignment 2, and when I have a chance to upload the Zoom video to Moodle, it'll be between those 2 files. And then this URL right here is well, I guess you can't see where I'm saying right here. But the thing on the right there where it says using LT Spice to verify behavior for an op-amp circuit or whatever, that's supplemental to homework 2 because I usually get a lot of questions about how do I do op-amp circuits in LT Spice. So I'm just trying to head that off at the pass and talk to you guys about how to use LT Spice specifically for the next few homeworks. Here's the submission portal. Then here's all the stuff for today. So here was the handwritten notes for positive feedback op-amp circuits. This first thing is a YouTube video on where I talk about positive feedback op-amp circuits and why we use them using LT Spice simulations. Then this second video is me working some problems on the board about deriving the equations for what's called the upper trigger limit and lower trigger limit for Schmidt triggers. Then we have the homework, and then the submission portal. And then for lecture 4, which is Thursday's stuff, this is based on negative feedback op-amp circuits. So then there's a video on solving a negative feedback op-amp circuit using the practical model. And then here's the homework set and all that kind of good stuff. And this homework set actually covers lecture 4 and lecture 5. So you'll get a slight reprieve on Monday and won't have a new homework assignment to worry about. So yeah, I'm trying to set it up on Moodle to where it's fairly easy to follow along with this online structure. So what like I said, I'm going to wind up doing is on the left here, instead of it going week by week, I'm going to have it go class meeting by class meeting so that and I'll even have the dates on there as well so that you know like when you're supposed to have looked at stuff by.
All right. Thanks.
Yep.
Thank you.
Huh? Any other questions?
I have one, maybe a stupid question. As far as the homeworks, is the final answer the only thing that's graded, or is like everything graded as a whole?
I go through the whole thing. So like I absolutely give partial credit. I feel like that's really what your question was about. So, I mean, I look at your final answer first to see if I need to bother going through stuff and finding your mistake and all that kind of jazz. But you know, if your final answer doesn't match my final answer, then I will go through and I'll make notes of, hey, you should have done this, or maybe this was an easier way to get it, or I'll just let you know, looks like all your work is fine, but there's a calculation error. And then I take points off or whatever accordingly. On the homeworks, I tend to grade them relatively quickly. Well, let me explain what I mean by that. I don't get your grades back to you quickly because I'm awful and I hate grading. So what I mean is I don't spend an awful lot of time grading the homeworks. On the tests, it usually takes me 45 minutes to an hour to grade each individual exam because I want to make sure that if you miss a part of a problem early on, and then that error gets carried through, you don't just lose like tons and tons of credit. So if you make a mistake at the beginning of a problem that influences later steps, I don't continue to penalize you for that mistake. I try to do that on the homework as well, but usually I'm in a hurry to get them done because like I said, I hate grading and I don't like to do it. So it usually takes forever for me to get around to it. And it's the end of the quarter and I'm trying to go like, oh God. So I'm going to try to be a little bit more proactive about grading this quarter just because there's significantly fewer of you taking the class than per usual. So maybe that will be an impetus for me to get off my lazy butt and actually grade things. We'll see. But yeah.
All right.
That remotely answer your question?
Yeah, that's pretty much everything.
Okay.
And I guess just in general for homework 1, are they all like verifiable in LT Spice?
There really shouldn't be any problems in this whole class that are not verifiable using LT Spice. Homework 2, problem 2 may not be, and what I mean by that is you can absolutely solve it, but if you use the practical op-amp model, it can't check to see whether or not you violated whether or not you're going to have saturation distortion. So you'll get the right answer, but then you'll have to go back in and say, all right, well, this answer is greater than the power supply voltages, so it needs to be kicked down to this value. But everything in homework 1 should, I don't want to say easily be verifiable because you don't have a lot of experience with LT Spice, but shouldn't take a whole lot of effort to get LT Spice to give you the answers that match your analysis. Do you have a particular problem that maybe your simulation isn't matching what you're expecting or something like that? Is that where these questions are coming from?
Yeah, the last 2, I haven't set up simulations for them yet.
Okay.
So I was going to go ahead and do that after class.
Okay. So one thing, there are multiple ways to set up circuits for the transient analysis problems. The easiest way, in my opinion, is to set the circuit up and run a DC operating point analysis to get your conditions at t is equal to 0 minus. Then what I would do is I would set up my initial conditions, and I think I talked about that a little bit in the first, let's see. Did I not do that? Hold on. That may be an issue. Let's see. Where did I put that video? That's homework one in the submission portal. I could have sworn I had it. Let's see. Well, I may have to fix something. Oh God, what did I just hit? Pretend you don't see how many YouTube videos I watch about video games and crap. All right, let's see, my videos. So this video, ELEN 223 syllabus comments and introduction, I actually set up a simple transient analysis problem in that. I don't know why I don't have a link to that on this thing, so I will put that up. And I will put it up in this May 31st to June 6th section, which will be class meeting 1, because that was what class meeting 1 was about. So you don't have to go through and find it all. I'll throw a link up where it should be. And it'll go through the steps of doing a DC operating point analysis as well as a transient analysis, so that you can see how to set up the initial conditions and all that kind of stuff, and B, how you can actually just input a mathematical equation and check that mathematical equation versus the simulation to make sure that your analytical solution is correct. So I apologize for not having that up where it was supposed to go.
All right.
Any other questions? All right, nobody's saying much anything. So I guess I will see you guys on Thursday. Have a good couple of days.
Ready to.
All right, you too.
You too.